Sulfides undergo a number of reactions. One is you can actually take a sulfide and treat it with a unhindered alkyl halide. So this is a methyl, which is unhindered halide. And the sulfide, the sulfur in particular, is nucleophilic enough, even without a charge, that it will attack and do an SN2 reaction. So attack this methyl and kick out the halogen as a leaving group. And we can actually isolate this charged ionic compound. So usually when we're doing organic reactions, we isolate neutral products. But in this case, we can isolate a salt. And it's all thanks to the fact that sulfur, even in its neutral state, is very nucleophilic, much more nucleophilic than an oxygen of an ether. And you can actually take this methylated material and use that as a reagent in a reaction. So if you were to treat it with another nucleophile, it could actually do an SN2 reaction to pick up this methyl and then kick out the sulfide as a leaving group. So in this case, this would be the leaving group. This reaction is important biochemically with the methylating agent SAM. You can also oxidize sulfides to either sulfoxides or sulfones. And the choice of oxidizing agent depends on whether you need to produce the sulfoxide or the even more oxidized sulfone. So if you're taking a sulfide and oxidizing it to a sulfoxide, one would use sodium metaperidate. And if you want to oxidize the sulfide all the way to a sulfone, you can use multiple equivalents of hydrogen peroxide, which would oxidize the sulfur past the sulfoxide all the way up to the sulfone. Something that's interesting about the resonance contributors of both the sulfoxide and the sulfone is that the resonance contributor that has no charge, right, which is this one for the sulfoxide and this one for the sulfone, is actually the least significant resonance contributor. So in both cases, the one where you see formal charge is the most significant resonance contributor, which is sort of strange because normally we want to minimize formal charge. That makes something more significant because it's more stable that way. But in this case, the charged structures are the most significant. And that's because if we really think about this pi bond, right, which are these second bonds from sulfur to oxygen, these are an overlap of a p orbitals that are different size. So the p orbital on oxygen is 2p, and the p orbital on sulfur is 3p. And because they're of different size, their orbital overlap is more minimal than if they were the same sized p orbital. So as a result, there's not a lot of pi bond character between the sulfur and oxygen, and therefore the structure more closely resembles the charged structures. And we noted that sulfides are pretty easily oxidized to sulfoxides and sulfones, and we can use this to our advantage in reactions. So if you recall, ozonolysis was discussed last semester. It's in chapter 8. And we have the process which produces a first and then a second what's called ozonide intermediate. And then after that's produced, it stays that way until you add dimethyl sulfide. And then the last step, the dimethyl sulfide reacts to form dimethyl sulfoxide. So it's essentially been oxidized, and thus we call it a good reducing agent because it's so readily oxidized. And what does it do in the ozonolysis reaction? We can first show these lone pairs on oxygen. And then sulfur will attack one of the oxygens in that's forming an oxygen-oxygen bond, because that's a weak bond. You can shift electrons over to form a carbonyl, form another carbonyl, and then form a lone pair at the end. So all of that's happening simultaneously to produce 2 carbonyls and DMSO, which is a byproduct of that reaction.